Right, good morning, everyone. So we were talking about broadcast channels and in particular degraded broadcast channels in the previous class. So I derived the capacity region of a general two-user discrete memoryless degraded broadcast channel. We saw that given any degraded broadcast channel, py1 given x, py2 given x, the capacity region of this broadcast channel is the set of all R1, R2 which satisfy R1 less than or equal to the mutual information between x, y1 given u, and R2 is less than or equal to u and y2. And this is for some, and this is taken over all possible pxu, where this auxiliary random variable u can be chosen such that the size of u is not too large. It is less than or equal to the minimum of the size of x, size of y1, size of y2 plus 1. Okay, so recall that a degraded broadcast channel is one where, so we say that y2 is degraded with respect to y1. If you can represent py2 given x as a composition of two channels, py1 given x and some other py2 given y1. If you can do that, then the two channel, then py2 given x is said to be degraded with respect to py1 given x. So in this class, we'll see that this capacity region for two-user broadcast channels extends to not just degraded broadcast channels, but slightly more general channels. Okay, and then we'll talk about Gaussian broadcast channels, and we'll see whether Gaussian broadcast channels are degraded or not. And we'll have a sort of separate proof of what the capacity region of the Gaussian broadcast channel is. So here, the complication is that the rate region is not just in terms of py1 given x, py2 given x, and px, but also in terms of an auxiliary random variable u. And this search for the right auxiliary random variable can be very hard, and even numerically evaluating the capacity region can sometimes be hard if the alphabet size is large. And more so, this is just the two-user degraded broadcast channel, remember. So if you want to generalize this to many users, then characterizing the capacity region would be even harder. All right. So in this class, I'll talk about slightly more general broadcast channels, not in full generality, but something which includes degraded broadcast channels. And then we'll switch gears and I'll talk about Gaussian broadcast channels and what their capacity region is. For the Gaussian broadcast channel, we'll have a closed form expression for the capacity region in terms of just the transmit power constraint and the noise variances. Okay, so any questions from the previous class? So,
General,
yes.
sir, we have considered the degraded channel currently, but
Mhm.
in what the channels will be? Will it be degraded or in practical scenarios?
So we'll see some examples of channels. So we'll first see Gaussian broadcast channels, which so we'll see whether they are degraded or not. But in general, so if you look at more complicated channels such as fading channels, these need not be degraded, and so the characterizing the exact capacity region in many cases can be very hard. But what is perhaps helpful is that this rate region for two user broadcast channels that hold over here, this region is okay, maybe not exactly this one, but the superposition coding in a bound, this is certainly valid. So this is not the complete capacity region, but certainly this region is achievable. All right. So even though we in many cases, in many practical scenarios, we cannot characterize the complete capacity region for a broadcast channel, we can still have reasonably good inner and outer bounds. And in fact, if you look at practical communication systems today, we're operating far below even these inner bounds. Right? Typically, you do something like, at least in previous generation cellular technologies, we were doing something a lot more simpler. Typically, something like equivalent to DDMA or FDMA, or essentially you're using orthogonal resources. But so certainly the rate or the set of rates at which we typically operate is below what can potentially be achieved. But there are other reasons why we may not be operating at either the superposition coding inner bound, or there are better inner bounds, and it's even so the superposition coding inner bound can still be achieved in a practical sense, because it's a fairly simple technique. Uh, there's nothing much complex. There's no sort of joint decoding done at the receivers. So for example, in superposition coding, user one first decodes the second message and then tries to decode its own message, whereas user two only tries to decode his or her own message. Whereas in for more general broadcast channels, this sort of successive cancellation decoding does not necessarily work well. Superposition coding need not work well. You could potentially, if you wanted to achieve a better rate, you would have to do something more complicated, and unfortunately, we're still not implementing those today. All right.
Yes, yes.
Yeah, so we'll see examples one after the other to see which ones are degraded, which ones are not. So in particular, I'll talk about two maybe practical classes of channels, not just broadcast channels, but also multiple access channels. One is, of course, the Gaussian broadcast channel. We've already seen the Gaussian multiple access channel. So these will turn out to be naturally degraded, but then in subsequent classes, I'll talk about fading channels, where depending on the kind of fading you have, the nature of the channel is completely different, and then you have not just questions about whether it is degraded or not, or what the capacity region is. We'll also come into questions of, is there something called a capacity region or not? But we'll get to that a little later, maybe in a couple of classes. All right. Any other questions? All right. So in the previous class, we saw one example channel, which was the two user binary symmetric broadcast channel, where user one sees the output of a BSC P1, and user two sees the output of a BSC P2. P1 and the two BSCs may or may not be independent of each other. It doesn't really matter. And for this, we have a computable capacity region. So R1 is less than H2 of alpha star P1 minus H2 of P1, and R2 is less than or equal to 1 minus H2 of alpha star P2. So by varying alpha from 0 to half, you'll get the entire capacity region. And we've plotted that in an earlier class. It looks something like this. Right. So this the region under the red curve. This corresponds to the superposition coding region, and also is so since it is degraded, this corresponds to the capacity region for the binary symmetric broadcast channel. All right. So it's this. So it's not a pentagonal region, which in many cases was true for multiple access channels for broadcast. Even for multiple access channels, it is not always pentagonal. But here this looks somewhat more complicated. Okay. So now that we've seen binary symmetric broadcast channels and degraded broadcast channels, let us see to what extent our results hold. So the superposition coding inner bound is obviously valid for any broadcast channel, whether it is degraded or not. But in fact, it turns out that superposition coding is optimal for more general channels, and and we can say that for two classes of channels, one which are called the class of less noisy channels, and the other which is the class of more capable channels. Okay, so all of these, so degradedness, less noisy channels, more capable channels, essentially correspond to channels where one channel is in some sense stronger than the other, and and the way you say one channel is stronger the other than the other depends on the definition. All right, so we said that a channel was one channel is degraded with respect to the other if you can represent the weaker channel as uh, as a concatenation of the stronger channel with some other channel. All right, and for a degraded channel, we've seen that the capacity of the degraded channel is always going to be, sorry, the capacity of the stronger channel will be larger than the capacity of the weaker channel. But if you have two channels where one channel is has a higher capacity than the other, then it doesn't necessarily mean that one is degraded with respect to the other. So for example, if you take a BSC 0.01 versus a BEC 0.5, it's obvious that the BSC 0.01 is going to have a lower capacity than the BEC 0.5, but the BSC 0.01 is not degraded with respect to the BEC 0.5. All right. So this, in some sense, really depends. So degradedness depends on the exact probability distributions, the conditional probabilities of the two channels. So a slight generalization of degradedness is this notion called less noisy. We say that Py1 and y2 given x, some broadcast channel, two user broadcast channel, we say that this is a class of less noisy channels, or in other words, we say that y1 is less noisy than y2. So y1 less noisy than y2 if the mutual information between u and y1 is greater than or equal to the mutual information between u and y2 for all distributions pxu. All right. So if this holds, we say that it's a class of less noisy channels, and we say that a class of channels p y1 y2 given x is more capable, or we say that y1 is more capable than y2 y2 if the mutual information between x and y1 is greater than or equal to the mutual information between x and y2 for all possible px. Okay, and the channel is if a channel is degraded, then it implies that it is a class of less noisy channels, and if it is less noisy, then it is more capable. But the reverse does not necessarily hold true. So let us see why this implication is true in the first place. Okay, so remember that p y1 y2 given x, so we say that y1 is less noisy than y2 if this set of mutual information inequality holds. Okay, and we say that the channel is degraded if the following holds. So x y1 y2, if this forms a Markov chain, then it is physically degraded. So let's look at physically degraded channels. Now if I introduce another u pxu, then the Markov chain structure looks something like this. Okay, and what this says is that so for a degraded channel, this holds. So u x y1 y2 forms a Markov chain. All right, and for it to be less noisy, the mutual information between u and y1 should be greater than or equal to the mutual information between u and y2 for all pxu's. Okay, so is it obvious that a degraded channel is also less noisy? And why is that true? So if this Markov chain holds, then can you say that this holds for all pxu?
Yes, sir.
Why is it true? So what property are we using over here?
Um, Degradation itself, like.
Correct. So you're using some fact of this Markov chain, right? If this Markov chain holds, then this mutual information is always going to be greater than or equal to this mutual information. So IUY2 is going to be less than or equal to IUY1. What property is that? It's some basic inequality that you have seen. So it's just the data processing inequality, right? Right. As long as you have this Markov chain, if u x, sorry, if u y1 y2 forms a Markov chain, then the mutual information between u and y2 is always going to be less than or equal to the mutual information between u and y1. That's what the data processing inequality says. Right? So this implication holds because of the data processing inequality. And this implication that if it is less noisy, then it is more capable. This naturally holds just by definition. So if this is true for all pxu, then it must necessarily be true for all px as well. So if iuy1 is greater than or equal to iuy2, then just by taking u equal to x, right? If you take u equal to x, then this inequality just reduces to this inequality, right? And it holds for one specific choice of pxu where x equal to u, right? So this implication is true just by taking x equal to u. Okay, so this chain of implication. So if it is degraded, then it is less noisy. If it is less noisy, it is more capable. So that holds, but the reverse need not hold. And again, I won't do it in detail. It's a little non-trivial to show it exactly, but here is an example channel where you have channels which are degraded, channels which are less noisy but not degraded, and channels which are more capable but not less noisy and therefore not degraded. Okay, and it's this simple class of channels. So take x. So suppose that y2 is the output of a BSCP, and y1 is the output of some BEC alpha. All right. So for some choice of P and alpha, the BSCP is degraded with respect to the BEC alpha. The reverse is not true. Right. So BEC alpha cannot be degraded with respect to the BSC P for any P between 0 and 1 and P 0 and half and alpha strictly between 0 and 1. Right? But the reverse can hold. Uh, the BSCP can be degraded with respect to the BECP for some choice of parameters. And in fact, this is the sort of choice of parameters for which it holds. So if alpha is between 0 and 2p, 2 times p, so basically we fix any fix a p in 0 to half. Okay, so if alpha is less than or equal to 2p, then the BSCP is degraded with respect to the BEC alpha. So the BSCP degraded with respect to the BEC alpha. Okay, but then if you increase alpha a little bit, so if it also obviously if it is degraded, then it is also less noise. Then obviously it's also a class of less noisy channels and also more capable. But now if I increase alpha slightly from 2p to anything between 2p and 4p into 1 minus p. So in this regime, the BSCP is not degraded with respect to the BEC alpha, but the BEC alpha is less noisy than the BSCP. So the BEC alpha is less noisy than the BSCP, but it is not degraded with respect to the BSCP. Sorry, the BSCP is not degraded with respect to the BEC alpha. Now, if I increase alpha a little more, then so if alpha is anywhere between 4p into 1 minus p and the binary entropy of p, then the BEC alpha is now more capable, is more capable than the BSCP, but it is not less noisy than the BSCP. Okay, so these are sort of generalizations of degradedness, and it turns out that the capacity region for all of these channels, for any class of channels which is less noisy or more capable, all of these have the same capacity region. So superposition coding is optimal for all of these classes of channels. All right, so superposition coding is optimal. It gives you the entire capacity region for more capable channels and also less noisy channels. And we've already seen that it is optimal for degraded channels. But for more general channels, so for channels which are not more capable or less noisy or degraded, superposition coding may or may not be optimal. So in fact, if you take alpha to be larger than, so if alpha is greater than H2 of P, then it is not more capable. Right? So for example, if H2 of P is less than alpha, then superposition coding may not be optimal. So you may need to do something different. And we can't really say exactly what the capacity region is directly. Okay, but as long as alpha is less than H2 of P, we know exactly what the capacity region is, and it is indeed exactly what we have derived previously. All right. Uh, any questions so far? So the problem of characterizing the capacity region of broadcast channels is really hard. Uh, so so earlier people only knew what the capacity region was for degraded broadcast channels, and and we only knew inner and outer bounds for more general channels. But then people slowly realized that some of these techniques can be generalized a bit, and so people slowly generalized it to less noisy channels and more capable channels. But but in fact, for channels which are not more capable, it's still an open problem. And in fact, even for more capable channels or less noisy channels, if the number of users is increased from 2 to 3 or 4, the capacity region, we still don't know if superposition codes are optimal or not. Uh, so so it's only for true user, more capable and less noisy channels. So maybe let me add this. So it's only for two user channels that superposition coding is known to be optimal. Okay, so a lot of things are open in terms of characterizing the capacity region of general broadcast channels, unlike the case of multiple access channels where we know what the capacity region is. Uh, for broadcast channels, it is still much harder, and in fact, even the proof. So note that we derived a converse proof for for degraded broadcast channels, but that proof does not hold for less noisy or more capable channels. For to show that superposition coding is optimal for more capable channels, you need a different proof, and a large part of the proof is still the same, except for identifying the right auxiliary random variable, right? And trying to find out what exactly the Markov chain structure is and how do you use uh, the notion of more capable and less noisy in the proof. And that is, it's hard. It is really hard. And the textbook gives a proof of the converse for more capable channels, but I'm not going to do that over here. Right? But in general, deriving converse proofs for general broadcast channels is a very difficult task, and the main difficulty lies in identifying what the correct auxiliary random variable is. So you need something which will give you the same rate region as the superposition coding rate region, or uh, for more general channels, there you can derive other inner bounds. So you want to identify the correct auxiliary random variable which matches with that of the inner bound. All right. So deriving good outer bounds is hard, but in some cases you can prove stronger inner bounds, stronger achievability results by using different techniques. So for non-degraded broadcast channels, there is what is called Martin's inner bound, and there's also Martin's outer bound. And and Martin's inner bound, in fact, does better than superposition coding for certain broadcast channels, which are obviously not degraded. But there are also results in the literature where you can do better than even Martin's inner bound for certain structured channels. All right. So if you're interested in knowing more about general broadcast channels, there are separate chapters dedicated to these topics in the El Gamal and Kim textbook. But we may not have time to discuss all of that, so I won't be going through it. But all you need to know is that the techniques that are used to derive inner and outer bounds are different for different kinds of broadcast channels. So a lot of people study certain specific classes of broadcast channels and try to derive inner and outer bounds for them, because even that is not an easy task. All right. So we know that superposition coding is optimal for these classes of broadcast channels. Okay, and since we know the exact, at least we have some closed form expressions for the capacity region, we can somehow plot it out, right? We can do it. We can evaluate it numerically and get a plot of what rate region is achievable. Okay, but for certain broadcast channels, it becomes even easier because you don't have to worry about auxiliary random variables. You can have a better closed form expression without any auxiliary random variable and without worrying about what pxu you have to choose. One case was, of course, the binary symmetric broadcast channel, where everything was in terms of the entropies of the binary entropies involving p1, p2, and alpha. And another class of maybe more practical broadcast channels are the class of Gaussian broadcast channels, where we can derive a nice closed form expression. In fact, it looks something much simpler. Okay, so recall that the two user Gaussian broadcast channel is the following. So you have X, the input X is passed through an AWGN channel to give you Y1. So it's AWGN with mean 0 and variance, let's say sigma 1 square, and it's passed through an AWGN channel with noise variance sigma 2 square to get the second receiver's output, which is Y2. Okay, and we have a power constraint to be satisfied at the transmitter. We impose that the energy of any code word, or in other words, the L2 norm square of every transmitted signal should be less than or equal to n times p for some parameter p, which we call the power constraint. Right? So this is the power. So this is the power constrained Gaussian broadcast channel, and and of course, so it's so we've seen the capacity region for degraded broadcast channels. So the question is this class of broadcast channels degraded? Okay, so what do you think and why? So is this class, so is this channel, if sigma 1 square is greater than, sorry, put it the other way around. So suppose that sigma 1 square is less than sigma 2 square, then is y2 degraded with respect to y1? So to show that y2, yes, sure.
So representing in terms of Markov chain and then computing the capacity, like
Okay,
how.
but even you don't even need to go to the point of computing capacity, right? So to show that y2 is degraded with respect to y1, you need to show that you can describe the channel from x to y2 as being equivalent to composition of the channel from x to y1 and y1 to y2. Right? So you need to, so you have y2, you have some channel from x to y1. You need to show that this is equivalent to taking the channel from, sorry, x to y2. This is equivalent to taking the channel from x to y1 and then corrupting it some more to give you y2. correct? And can you always do that in this case?
Yes, yes. Sigma 1
Uh-huh.
square is less than sigma 2 square.
Yes. So what is this channel that you would choose?
It should also be a Gaussian.
Uh-huh. And
Uh,
with what variance?
Variance should be greater than, sorry, it should be less than sigma 2 square minus sigma 1 square, something like that.
Not less than, right? It should be equal to sigma 2 square minus sigma 1 square. So you
Uh,
want to show that this is equivalent to some other
and
channel,
then, yeah, it should be, sorry,
correct?
yes, it should be equal to sigma 2 square minus sigma 1 square.
Yeah, so this channel is basically an AWGN channel. So you have X, Y2, let's call this Z2, and Z2 is Gaussian with mean 0 and variance sigma 2 square. And the first channel, that is X to Y1, is AWGN Z1, which is Gaussian with mean 0 and variance sigma 1 square. And now if I add an independent Gaussian random variable, let me call it Z2 tilde, which is Gaussian with mean 0 and variance sigma 2 square minus sigma 1 square, then the sum of these two, Z1 plus Z2 tilde, is going to be Gaussian. Z1 plus Z2 tilde is obviously a Gaussian random variable, and it has mean 0 and variance sigma 2 square. Correct? So this channel is equivalent to this channel over here. Right? And therefore, no matter what the exact values of sigma 1 square and sigma 2 square are, as long as sigma 1 square is less than sigma 2 square, channel 2 is always going to be degraded with respect to channel 1. Right? And and in fact, for take any set of channels, any number of users, irrespective of what the noise variances are, as long as the noises across each channel are independent of each other, this is always going to form a set of degraded channels. You can always order the channels in terms of degradation, because you can always pick the smallest sigma 1 square, the next smallest, or take the smallest noise variance, the channel with the smallest noise variance. That is going to be the strongest channel, and every other channel is going to be degraded with respect to this channel. And sort of the worst channel, that is the channel with the highest noise variance, is going to be degraded with respect to all of the other channels. Right? Just by the property that the sum of two independent Gaussians is going to be another Gaussian random variable. Okay, but note that this holds only if the two Gaussians are independent of each other. Right? So this can be slightly generalized. So even if there is some channel coefficient, some known deterministic channel coefficient, then it reduces to essentially the same channel, because you can just plug it into P or sigma 1 square. Right? So even if we have, let us say that we have the following channel, you have X, uh, let's say this is H1, H2, or maybe, yeah, this is Z1, this is Z2, give you Y1, Y2. Then this channel is essentially, if H1 and H2 are known to both the transmitter and the receiver, then the capacity region of this channel is the same as the capacity region of this channel, which is Z1 by H1 and Z2 by H2. All right. So effectively, it just so here, so this is a Gaussian random variable with mean 0 and variance sigma 1 square by h1 square, and this is Gaussian with mean 0 and variance sigma 2 square by h2 square. Correct. So as long as h1 and h2 are deterministic quantities and are known to the transmitters and the receivers, then looking at this channel is the same as studying this particular channel. So it's enough to just study this particular channel for some sigma 1 square and some sigma 2 square. Correct. But note that if the channel coefficients are not deterministic, if they're random, and in particular if they can vary across time, then things change, and that is what we call a fading channel, which we will study in subsequent classes. Okay, but now we are only going to focus on this Gaussian two-user Gaussian broadcast channel. Okay, and the two-user Gaussian broadcast channel is always going to be degraded. All right. Any questions? Okay. So for degraded channels, we already know what the capacity region is, but in fact, we'll do a slightly separate, a different approach. We'll take a different approach in deriving the capacity region. So this has a much nicer expression of the capacity region of the two-user Gaussian broadcast channel, and the capacity region turns out to be the set of all rate pairs which satisfy the following inequalities. So R1 is less than or equal to half log 1 plus alpha p by sigma 1 square, and R2 is less than or equal to half log 1 plus 1 minus alpha p by alpha p plus sigma 2 square for some alpha varying between 0 and 1. So as you vary alpha from 0 to 1, this varies from the capacity. You get the complete capacity region for the two-user Gaussian broadcast channel. Okay, and the achievability is of course using superposition codes, but just by looking at this expression, can you sort of think and tell me what this might look like? So suppose you had to achieve this capacity region using two different code books. Okay, so all you know at this point are how to achieve the capacity region of the point-to-point Gaussian channel. So again, I'm doing this a bit heuristically, but intuitively, can we get the above using capacity achieving codes? Actually is going to be Gaussian code books. For single user AWGN channels. Right? So let us say that we know how to design a capacity achieving codebook for single user AWGN channels. Okay. Just by looking at this expression, can you think about how you would design a code for the two-user broadcast channel? Any hints? So the alpha should sort of give you a hint. So alpha is something between 0 and 1, and this looks like something, and this is something else. So you have an alpha, you have 1 minus alpha, and the total power constraint is P.
Sir, are we talking about how we'll be picking alpha?
No, so let's say you pick some alpha. Okay, so pick any alpha. So pick an alpha, let's say 0.5 or whatever. So that will give you some R1 and R2, right, for a given P1 sigma 1 square and sigma 2 square. Now, having chosen this, how would you achieve these rates? How would you design code books for which the probability of error would vanish with n? And I want you to do this using code books designed for single user AWGN channels or point-to-point AWGN channels. Okay, so here let me give you a little more hint. So suppose that I can, so for any let me say P tilde and sigma tilde square, I can construct a code book. Basically, I can construct a code for the channel with power constraint for the AW for the point-to-point AWGN channel with power constraint P tilde, noise variance sigma tilde square. Okay, so this is the AWGN code book for whatever the capacity achieving code book. The capacity achieving AWGN code book. Right, so this operates at rate close to half log 1 plus P tilde divided by sigma tilde square. Okay, so using these, I need to essentially construct two code books, one for user one which is intended for the message of user one, and the other which is intended for the message of user two. Okay, and then I need to somehow combine these two together so that user one can decode his message and user two can decode his or her message. Correct? So what does this suggest? What should you do for user one? So note that the channel from the transmitter to user one is an AWGN channel with noise variance sigma 1 square. Any ideas? So think about power allocation for the two users, right? You have two users, and you need to somehow allocate resources for these two users. So you need code books for user one and code books for user two, and you have a finite power constraint of P. And obviously, if I allocate all of this power for user one's message, user one's transmission, then I won't have anything left over for user two, right? So, so let us say we do the following. I allocate alpha p amount of power for user 1's codebook. Okay, so basically I use an AWS capacity achieving codebook for with power alpha p. So basically every code word from this codebook is going to have L2 norm less than or equal to n times alpha p. And this is of course designed for uh, the AWGN channel with noise variance sigma 1 square. Okay, so this is the amount of power that I'm going to allocate for user 1. All right, and I'm going to allocate the remaining power for user 2's codebook. Allocate remaining, so 1 minus alpha times p. So the sum of these two powers is going to be equal to the total power constraint that you have, which is p. All right, for user 2. For user 2, right? But now what is user 2 going to see, right? So remember that user 1 is going to do the following. So for user, so anyway, so allocate the remaining 1 minus alpha p for user 2's codebook. But remember that user 2 has to decode only his or her own message, but but the but he's going to do it by treating the other code word as noise. All right. So let's suppose that we use 1 minus alpha fraction of the power to design this part of the code book, and we're going to design it for a larger noise variance of sigma 2 square plus alpha times p. Okay. So what does decoder 1 do? So decoder 1, okay. So these are the two code books, and then for transmission, so the actual xn is going to be x1n plus x2n, where x1n is going to be drawn from this code book, and x2n is going to be drawn from this code book. Right? So you want to transmit M1 and M2, the messages corresponding to for each user. You transmit just the sum of the corresponding code words. Since these code books are independently chosen, the total power constraint is still satisfied. So each of these code books satisfy their individual power constraints. So the transmitted code word also satisfies the power constraint of P. Okay, and so that is what the transmitter does. The receiver, so receiver 1, it first, basically what it does is successive interference cancellation. So first decode x2n, right, by treating x1n as part of the noise, right? So y1n is x1n plus x2n plus z1n. So you have to decode x2n, assuming that x1n plus z1n is noise. And what is the total variance of the noise in this case for decoding only x2? So z1n tilde is x1n plus z1n. What is the variance? Yes. So it's the sum of the variances, right? Which
P,
is what?
yes, sigma P will also be there, right?
Correct. So it's
Sorry,
alpha
alpha P
p
plus sigma 2.
plus sigma 1 square, right? So it's for user 1.
Mhm.
All right. So decoding succeeds as long as the rate is less than, so you can recover x to n as long as the rate is less than half log 1 plus the power of x2 is 1 minus alpha, r2 is less than alpha p by alpha p plus sigma 1 square, which is already true. We're taking r2 to be less than half log 1 plus 1 minus alpha p by alpha p plus sigma 2 square, which is larger than sigma 1 square. Right? So x2 can be decoded uh, uh, without any error or with vanishingly small probability of error. And now you remove the component of x2 from x1, remove x2 hat. So look at y1n minus x2n hat, which with very high probability is going to be just x1n plus zn. And now decode the first code word, the one which you're actually interested in. So this is an AWGN channel with noise variance alpha p by sigma 1 square. So decoding succeeds with high probability as long as R1 is less than this, the capacity of this particular channel, and that is anyway guaranteed over here. So it's also R1 is less than half log 1 plus alpha p by sigma 1 square. Okay, so that's great. So decoder 1 can decode successfully. Decoder 2 does essentially the same. So decoder 2 sees y2n, which is x1n plus x2n plus z2n. It reads x1n as part of the noise, so it wants x2 and this has variance equal to alpha p plus sigma 2 square. So as long as R2 is less than half log 1 plus 1 minus alpha p by alpha p plus sigma 2 square, decoding succeeds with high probability. All right. So this lets you achieve the following rate. So just by using this sort of superposition code and successive cancellation decoding, you can achieve any rate pair which satisfies this. All right. So you can treat alpha as sort of a power sharing random variable, like the time sharing random variable we had. So alpha decides how much power is allocated to user one's codebook and how much power is allocated to user two's codebook. Okay, so if you take alpha equal to 1, then essentially only user 1 is transmitting all the time and user 2 gets to transmit nothing. There's no power for user 2. Whereas if you let alpha to be equal to 1, then alpha is equal to 0. Sorry, when alpha is equal to 0, then it's only user 2 who gets all the power. Whereas if alpha equal to 1, then it's only user 1 which gets all the power and he's operating at his full capacity. All right. So alpha is sort of this power distribution parameter. All right. And just by varying the amount of power for the two code books, you can in fact achieve the entire capacity region for the two user Gaussian broadcast channel. All right. I guess I'm over time. So let's stop at this point. Are there any questions?
So this is NOMA only, which we have discussed currently.
Exactly. So this is non-orthogonal. It's okay. Yeah. It's a broadcast channel, but in fact, yeah, it is non-orthogonal transmission, right?
Oh,
You're both of them are transmitting simultaneously at the same time, but you're distributing the amount of power you have among two different users.
yes, yes.
Right, and it's you can think about how to generalize this to more than two users fairly easily. It should be fairly intuitive. So you decide some order of decoding. So R1 should be less than or equal to half log 1 plus maybe alpha 1 p by sigma 1 square. R2, to decode the second user, you treat the first user's component as part of the noise. So half log 1 plus maybe alpha 2p by alpha 1p plus sigma 2 square. And R3 would be less than or equal to half log 1 plus alpha 3p by alpha 1p plus alpha 2p plus sigma 2 square, and so on. All right, where the sum of all the alpha i's should be equal to 1. And that gives you the rate region using this approach.
Yes.
Okay, any other questions? Okay, so let's continue in the next class. So see you next week.
Thank you.